So now, next we welcome Professor Adrian Barbu, who is from Florida State University, United States. Professor received a PhD in mathematics in 2000 from Ohio State University and a PhD in computer science in 2005 from the University of California, Los Angeles. From 2005 to 2007, he was a research scientist and later a project manager in Siemens Corporate Research, working on medical imaging problems. He received the 2011 Thomas A. Edison Patent Award with his Siemens co-authors for their work on marginal space learning. In 2007, he joined the statistics department at Florida State University as an assistant professor, and since 2019 as a professor, he has published more than 70 papers in computer vision, machine learning, and medical imaging, and he has more than 25 patents related to medical imaging and image denoising. He has wrote a book with his PhD advisor, Song Chuanzhu. The book is titled Monte Carlo Methods and was published in Springer in 2020. The title of his keynote talk is Organ Segmentation, a Journey from Level Sets to Shape Denoising. Welcome, Professor.
Thank you. Okay. So thank you for inviting me and for this conference. And this work is a joint work with my former student Orhan Akal and my current student Cheng Long. So let's get started. So we're gonna talk about organ segmentation, and at the end we're gonna get to denoising kind of things similar to the diffusion models, but not exactly. So for this work, we start with the Chan-Wesse algorithm, which involves a level set with length-based regularization. And at the same time, it infers models for the interior and the exterior of the regions. So the Chan-Wesse has this, is based on this for Shah energy. So the energy of the contour is, so it wants to have a constant model inside and a constant model outside, plus the length-based regularization. But it's hard to evolve the contour directly. So you could maybe do that, but then you have these self-intersection problems and holes and so on. So a better approach is the level set approach, and that's the Chan-Wesse. So it's not only this energy function, but an extension to level sets. So instead of using directly the curve, we represent the curve as the zero level set of a surface. And then we extend the energy as the energy of the level set. So here you see the three parts, and we have here this Heaviside function to represent, or a smoothed Heaviside function to represent what is inside and what is outside the curve. And the length-based regularization is replaced with this part. And here there is the smoothed Heaviside, so it's a smoothed version of the step function, and its derivative is a little bump instead of the delta. And then to minimize this energy function, we want to solve this Euler-Lagrange equation. So the function that minimizes satisfies this Euler-Lagrange equation, and that this Euler-Lagrange equation can be done. The solution can be reached iteratively by this update. And at the same time, while this update is iterated, the parameters for the interior and the exterior are obtained as you see here. So what we did is we took this level set update where we have these models for the interior and exterior of the image, and here is this curvature-based term which does the length-based regularization, and we said, let's have a better regularization instead of just length-based. Let's train a neural network for this regularization. So then we have this iterative algorithm that starts maybe with some initial level set and updates in a similar way, but here is the neural network. So we have here a diagram with the whole thing. And at each iteration, we obtain a better and better segmentation. But now this shape parameter, instead of just being length-based regularization, it's specific to an object. So it's like a lever shape parameter. So that's what we did. And but now the problem is how to train the whole thing, because the whole evolution is a recurrent neural network. So we do it in an end-to-end fashion by backpropagation. So for the loss, we use the combo loss, which is has the cross entropy loss and the dice loss. And the backpropagation is called backpropagation in time, because so you have this recurrence, right? And so basically we unroll the neural network a certain number of steps. That's we say we're gonna run the iterations a certain number of times, t steps. So then we have the same neural network applied t times, the same parameters, and if we would do backpropagation, we would have a gradient with respect to each of them, and the total gradient is the sum of these gradients. And yeah, so these are the details, and to train. So now we want to apply this to medical imaging, to organ segmentation, and we want to have a good initialization, and we do that by this pre-processing step, which is a pixel-wise detection. So we use a fully convolutional network with a certain number of layers that will give us a detection map, pixel-wise. So, and then, but this detection map, while it's good at capturing the organ that we want, it has a lot of artifacts like isolated, spurious pixels. And we observed that if we compute this probability map, which is based on the detection map, so we get this binary mask, and we basically do a histogram, and for each bin of the histogram, we look how likely it is to be in the foreground or in the background, and this way we obtain this probability map, which, as you can see, it follows the organ much better. It also has some other artifacts, but at least it's more accurate. And then we use this probability map as the data term, the image for our Chan-Wese. So these are the details for how what neural network we have, and we need to have padding. So this is a fully convolutional network. We need to have padding such that the input is the same size as the output. And then how to train. So now we have, so if you look at the whole neural network, we have two inputs. One is the initialization, and one is the image. So this image that you see here is the probability map. And now we have initialization, and we need to train the neural network to be resilient to give us a good result from all kinds of initializations. So that's why we do many types of initializations, such as the detection map or the thresholded probability map with different thresholds, or we take the ground truth and distort it like this. And we train to obtain the same result from all of them. And here is an example of all these details. So we have the input image, the probability map, then the initialization, and the segmentation obtained after 3 steps of this Chan-Wesse neural net and the ground. And here you see the level set during those 3 iterations. And this result is the 0 level set. And we experimented with livers and horses. And we used the dice coefficient to evaluate. And for the livers, so we start with a dice of 90, so based from the initialization with that detection, and we get 94 dice with 3 iterations. And for the horse, we start with something less than 50, and we get to 68. And if we compare with the actual Chan-Wesse, which only has length-based regularization, is not as good. And it needs like 100 iterations where we need only 3. And now we want to make it even better and introduce a U-net instead of just a fully convolutional network as the neural network. So to give us that shape-based regularization. And the U-net can be 2D or 3D. And it only has a few parameters because it only has 2 convolution blocks and each block with 2 convolution layers. So it only has 350,000 parameters as opposed to a regular U-net, which has 50 million parameters. And so now we do the same thing in 3D, and we have the initial segmentation and the input, which is also a probability map, but now in 3D. And we get the segmentation with the same type of iteration. And to evaluate, we use this data set from Gibson and all from 2018, which has 90 CT scans, 43 from the pancreas CT data set, and 47 from the BTCV. And some of the BTCV patients have metastatic liver cancers or other abdominal pathologies, so it's a more challenging data set. And so we have so the 3D it requires a lot of memory, so we only can work with 128 by 128 resolution from the 512 by 512 input. So, and then we also work at 256 by 256 with just a CNN instead of a U-net to refine the result from 128. And here is an example of a result, a 3D result with the 3D CVNN, so at the 128 resolution. So here first the detection map, the probability map, and the segmentation, which is obtained after 4 iterations, and the ground. And as I said, the CVNN, we will take this result at the 128 resolution and refine it at the 256 resolution with only 592 parameters, just a few parameters. And it will give us a more accurate result. So this is the whole diagram of this approach for organ segmentation with the detection, then the 3D CVNN U-net, which gives us at the low resolution a segmentation, and then the final result is obtained by this 3D CVNN, which only has a CNN. And we compare with all kinds of other papers, but not all of them are on this data set because some of them are on other data sets. So here, this with the 9 folds are on the same data set, but they are a little bit older results. So our result at 128 resolution is 95.6 dice, and the whole approach at 256 resolution is 95.2, but it has a smaller boundary error. And then these are some recent methods based on transformers or this deep implicit shape model, but this is only tested on one fold on 13, these two, NNUNet and DISSM, on only 13 volumes. Whereas our method is with cross-validation tested on 90 volumes. We use four-fold cross-validation. So it works pretty well. And we looked, so do we need all this? Do we need the 3D? Do we need the UNet? So we did an ablation study to see how important different parts are. We start from the same initialization. And if we only do 2D, we get 93.68. If we use the UNet, we get a little bit better in 2D. If we use the 3D, but no UNet, doesn't work as well. And if we use both, we get the 95.50. So both the UNet and the 3D are important. And also the computation time, I wanted to show you that our method is very fast, only less than a second, whereas these recent methods are more than 10 seconds. So we saw this Chan-Wessel neural network, which has this update equation. And the important part is this UNet, which helps update the level set. But it's like we train this whole UNet to work on the whole level set, but what matters is only the zero level set. And the input is also corrupted type of what we want. And this neural network is trained to recover from this corrupted shape. So the question is, how can it work? Maybe, how well could it work in one step and without the data? So we call this task shape denoising, and we want to see all kinds of noises, corruptions of the shape. And now we're going to work on horses instead of levers, and in 2D instead of 3D. So we represent these shapes as binary images of a certain size. And right now the shapes are all aligned. And we want to study this shape denoising where we corrupt the shapes by noise and we would like to denoise them. And in a way, it's similar to this post-denoising autoencoder from 2020, where they used this idea, which also was present here in our corruptions. So they corrupted the ground truths and trained the denoising autoencoder to recover the true segmentation. But we will show more types of noise, and we will evaluate 7 shape modeling methods, not only the UNet. So here is the problem. So we have an original shape. We introduce noise in some ways when we show different types of ways introducing noise. And we would like to denoise this to get back to the noisy shape. And all the shapes are aligned and inside an image of 128 by 128. And so here are the 6 types of noise that we're going to discuss. The salt and pepper noise, the circle noise that you already saw, the real image noise, the occlusion noise, the detection noise, and the threshold probability noise. So the salt and pepper is the simplest. We just flip pixels to its opposite value with a certain probability. The circle noise, we add these semicircles or holes on the boundary, and the radius of the hole is related to the level of noise. The real image noise actually replaces the black background with a thresholded real image. But this way we cannot control the level of noise, but we can get thousands of such images, and then we see what level of noise by looking at the die score of, or the intersection of a union. The occlusion noise does kind of similar, but with the foreground. So we take a real image, threshold it, and use it to occlude the foreground. So it's like the object is behind this occluder. And these two are very important also in medical imaging. So this one is related to maybe there is some things in the background that have the same intensity or as the foreground. So we would like to get rid of them. And this one is about maybe the organ has a tumor or some other artifacts that make it have holes. And so we would like to get rid of those artifacts when we do the segmentation. And then the detection image noise is actually, we use the trained neural network, the pixel-wise detection, and whatever result we obtain, we say that that's the original shape with some noise, which is the detection image noise. And then the threshold probability map. So you saw the probability map is the same probability map, but here we obtain it from the ground truth. And then we threshold it with different thresholds. So the probability map is shown here, and here with different thresholds, we get different levels of noise in the foreground or in the background. So these are the types of noise that we are going to investigate. And we're going to look at two data sets, the horse data set and the CUB 200 birds data set, where you use 7 species of flycatcher birds with 417 images. And 200 are for training and 210 for test. And for the horse, 159 images for training and 168 remaining images for test. And we're going to use the intersection over union, which is a more demanding measure than the dice coefficient. And here is the data sets that we put together for the different types of noise. And for some of them, like salt and pepper, real image, it's easy to get a lot of images at different levels of noise. And we measure the level of noise by the IOU between the noisy image and the ground truth. So here we have levels from 0.5 to 0.9. But for the detection image, whatever we obtain as a detection is the image, so we don't have too many. And for the probability, we have a few more. And we're going to evaluate many methods that can be used on these binary images. And some of them, I don't know if they have been evaluated for this kind of applications before. So like the deep Boltzmann machine, the centered convolutional DBM, the energy-based model, and the masked autoencoder, and the deep lab V3, besides the unit. And the masked autoencoder is quite interesting. It uses a transformer, and it's trained to, its self-supervised learner is trained with masked images to recover the original image. And so some parts, some patches are masked, but the autoencoder is given what locations are masked. And by the transformer architecture, he can only use the input that is not masked and still obtain a full output. And we trained it for the purpose of this image denoising. And for training, we used, so these are the test images, but we have a similar set of training images, and we used all of them for training, and with all kinds of perturbations. And so here are the example for the salt and pepper noise. So the active shape model, which is quite old-fashioned, but we would not wanted to see how well it fares with all these modern methods, doesn't do a very good job. And if you look, the best are the UNet and the masked autoencoder. And here we have curves for each method for the different levels of noise. And the masked autoencoder and the UNet are on top, and they can obtain even from a 0.5 IOU, they can get us to about 0.95, both for birds and for horses. And the ASM, active shape model, is the worst. And here we don't have it because we don't have clicked points around the shapes of the birds. And the DBM is the second worst. And for the circle noise, these are examples of results. And again, the UNet and masked autoencoder are the best. And same thing is shown by the plots. And for the birds, seems that the masked autoencoder is better than the UNet for this circle noise. And if you look at 0.5, is not as good as the salt and pepper noise. It only can get us to about 0.85. The real image noise, yeah, and here is an example of result. And here are the curves. And again, the masked autoencoder and the UNet are the best. And the occlusion noise, again, masked autoencoder and the UNet are the best. And for detection image, the masked autoencoder and UNet are the best for horses, but they can only get us to about 0.8. And here the DeepLab V3 Plus is also very good for the birds. And then the threshold probability noise. Again, masked autoencoder and UNet are the best. So what did we see? We see that the masked autoencoder and the UNet are the best shape denoising methods, and DeepLab V3 is the third best. And the energy-based model outperforms the convolutional DBM, especially when dealing with real image noise. And if we look at the noise types, the salt and pepper is the easiest, followed by real image noise. And the circle noise and occlusion noise are more challenging. And the most challenging is the threshold probability noise and the detection image noise, which are the ones that we actually need for segmentation. So in conclusion, we started with this method for object segmentation called Chan-Wesse neural network that generalizes this Chan-Wesse level set, where we replace the length-based regularization with the trained CNN, which is trained by backpropagation in an end-to-end fashion. And we obtained good results competitive with the state-of-the-art for liver segmentation in 3D. But we used these multiple types of initialization to avoid overfitting. And these initializations led us to this shape denoising problem, where the shapes are represented as binary images, which are aligned, and we introduced different types of noise. And if you look, these noises are, most of them, except for the salt and pepper noise, are more challenging and structured in different ways than just Gaussian noise. And we evaluated 7 shape modeling and denoising methods, and we saw which ones are the best. And in the future, we plan to study shape denoising in the wild, where the shapes are not aligned, and methods for training this denoising in the wild, where we can have aligned shapes or methods trained on unaligned shapes, which each has their own challenges. And then we would like to come back to the CVNN and apply all the things that we learned to object segmentation, more challenging object segmentation problems. Thank you.
Thank you, Professor Adrian. So I will now move to our attendee. Does anyone have any questions?
Yes, I do have a question. Hello. When you mentioned the UNet, is that a pre-trained or you train the new UNet from the very beginning?
We trained the unit from the beginning because it's a smaller unit with only 350,000 parameters instead of 50 million. And we trained it with all the types of noises that we used in practice.
Okay, so it still have the better result than the convolutional neural network. Okay, I get it. And then about the convolutional neural network, you mentioned you didn't use ReLU, you used the ELU. Is there any particular reason?
Just experimentally, we observed it works better, and actually on other experiments, recent experiments, we observed similar things.
Oh, okay.
So
Thank you
probably
very
it works
much.
better for this kind of autoencoder problem.
Oh, thank you. Thank you very much. I have no more questions.
Okay, so do we have any other questions? If no more questions, or maybe if you can think about some question later, you can drop an email to Professor Andrew. So thanks again, Professor.
Thank you for inviting me.
Thank you. And now